Hi everyone. In this video, we're going to pick up where we left off last time, and that's with something called probability mass functions. So, just as a refresher, if we go back, what we were doing in the last video was we were looking at probability distributions, and specifically, we're going through an example here of how we can use this probability distribution to answer probability questions. And as another example or another reminder, a probability distribution is the collection of all possible outcomes of a random variable, capital X, and so those outcomes are little x, and then their associated probabilities. And so we see the collection of all of the possible outcomes in the top row of this table, and then the probability of each happening down here. Okay, and so that's sort of what we're thinking, or that's how we're going to think about a probability distribution right now. Okay, and so what we're doing in this video is once we go through here, is we're thinking about the sort of separate parts of a probability distribution, because the probability distribution is sort of an overarching idea. It seems kind of concrete now, but we could take a very theoretical viewpoint towards it if we wanted. Okay, but we won't really in this class. But we do need to sort of know the parts that we're dealing with. And so there's a number of things that we can create for a probability distribution. Okay, and specifically we're talking about discrete ones here. So just to keep that in mind, we have a countable number of outcomes that we're working with. Well, anyway, the collection of probabilities for the corresponding values of the random variables is called the probability mass function, or PMF. Probability mass function, or PMF. Okay, and so, for example, this was our probability distribution table that we were working with in the last problem. The PMF part of this distribution is the second row. Okay, so the second row, the probability that x equals x here, is the probability mass function. And so it's a function like any other sort of function that we are working with. We can input an x, so it's kind of the second line, it's kind of the whole thing. But we input an x really up here, and then the output of the function is one of the possible values down here. Okay, and so it's a function like anything else. It's called a probability mass function because it follows a sort of physical idea that we'll talk about, a physics or physical idea of probability, that at each point, so it's about probability, of course, okay, and that at each outcome of the random variable, we place essentially a point mass at that function, or at that outcome. And so the outcome happens at, it happens at 2, at 3, at 4, so on and so forth. And so essentially there's a point mass at each of the possible outcomes. And I know that probably seems a little opaque, but it'll make sense, especially when we go in the next chapter and talk about continuous probability distributions. Okay, because we are no longer having mass at single points. We're having something totally different. But anyway, the PMF really is sort of the second part, first and second rows of this table. You can think about it like that. A PMF, and this is what I said before, places a point mass at each possible value of the random variable and 0 everywhere else. And so this is important, okay, but it's also kind of intuitive in context when we're actually doing something. So in your turn, I'm going to ask you to write out this table for rolling a fair 6-sided die. Okay, and so you're going to have to write this out, write out the PMF and answer probability questions, so on and so forth. And in the context of rolling a die, the only possible outcomes are 1, 2, 3, 4, 5, and 6. So there's no possible outcome at 3.5 or 4.7 or 0.1. So those don't happen. And so the probability, of course, that those will happen. So for instance, in our example above, it's really the same thing, but the probability that x equals, say, something like 2.2, that's 0. And that should make some sense, but it might be helpful, and hopefully it'll be helpful, if we look at it graphically. Okay? And so this is an xy plane, okay, and this is a different example in your book, so don't get worried about the y's and p of y, so on and so forth here. Okay, the y is the outcome of, a random variable. It's one possible outcome, and the outcomes can apparently be 1, 2, 3, or 4. And on the y-axis of this graph, even though it's y is on the x-axis, and then probability that y happens is on the y-axis. And so this is, with the probability that each of the points will happen here. On the y-axis, you'll see that at each point there's a point mass there, and everywhere else it's 0. Okay, and so that's what it looks like graphically, and maybe it helps to hammer some of these points that I've been talking about home. So the conditions of a PMF. Okay, and I should make clear here that we're going to call the PMF little f of x, so lowercase f of x. The book likes to use p, as in this picture up here. They use p of y. I'm going to use lowercase f, okay, in my examples and everything that I do. So you can choose either. I'll know that you mean the same thing, and you'll see why in just a second why I choose little f. But anyway, that's what we call the PMF. It's a function, right? And so f of x. Okay. The stipulations or the conditions that need to be true for the PMF to be true is that any probability has to be non-zero, has to be non-negative, 0 or positive. So it has to be positive, and they all have to sum to 1. And so that means that each of these entries up here need to be positive, and when I add them all together, not the 1, 2, 3, 4, 5, and 6 above, but when I add all the probabilities together, I should get 1, or I need to get 1. If these two things don't hold, then it's not called a probability mass function. Okay? So that's a PMF. Now we get to the your turn that I was talking about in the previous video. And so consider the experiment rolling a fair 6-sided die, and let the random variable x equal the value on the face of that die. And answer the following. So first, I want you to make the probability distribution of x. So write it out in a table like I have done in the last few slides. Okay? And then answer the following questions. So what's the probability that you roll a 4, at least a 3, at most a 4, and then 2.5? Okay? And so try to answer those on your own. And so then after you're done, continue on with the video. Okay, so we're going to continue on for just a little bit longer. So we have one sort of property or one sort of thing that a probability distribution has, or rather I should say a discrete probability distribution has, is a PMF. Okay, it also has a CDF, or it should. Most of them do. Okay. It should have a CDF. or a cumulative distribution function. Okay? And it also may seem weird that, like, I was talking about a function and then it's like a table, and we're not used to seeing functions as tables, although there's nothing that says it can't be. What we're used to is like a functional form where I have a formula and I plug in or I substitute in a number and then something comes out. We've worked with tables so far, but we will in fact get to functions, and so that's coming, and it might seem a little more natural to work with formulaic type things. But anyway, so far we've had nice examples where there are only a few outcomes, but in many cases, sort of in the real world or what you might deal with, the number of possible outcomes of the random variable are very large. So this is sort of a practical point to a very theoretical reason. Now, this is going to be like a practical point that'll help us try to understand what a cumulative distribution does. But a cumulative distribution means so much more in a probability course that like isn't sort of germane to our discussion. So what I'm saying is this is very important. We'll only see a small part or a small use of it. So, for instance, if we asked a probability question of at most or at least with a variable that, say, had 10,000 possibilities, it would take me a long time to add up all the possibilities. So, a 6-sided die, it's not that hard to add up, at least 3. You've got 3, 4, 5, and 6, and we can add up 4 numbers. But if I had a 1,000-sided die, or maybe a 10,000-sided die, and it wasn't equally likely, or we just had, some other question where we have all these outcomes, and I actually have to add up, 5,000 numbers. That's not going to be nice. Okay? We have a computer, and the computer can do it instantaneously, but if we're doing it by hand, it would take us forever. And so what we can use is something called a cumulative distribution function. And what a cumulative distribution function of a discrete random variable x with a corresponding PMF f of x is it looks like this. Okay? Notice the difference. So to be thorough here, I put more of a formal definition. I have a discrete random variable x, and it has a corresponding PMF f of x. Okay, so I have that first thing. Then the CDF is defined as uppercase f. So notice the difference between PMF lowercase f, CDF uppercase f. Okay. The CDF is the probability that x is less than or equal to x. So the random variable, so it's the probability that a random variable x is less than or equal to a lowercase actual something that I saw. Okay, and I could write that in summation form with a sum where I'm adding up, and what it's doing is it's accumulating, and I know I've written that terribly there, but it's accumulating probabilities less than or equal to x. So it's accumulating probabilities for values of x that are less than or equal to x. So that's the CDF. Okay, it just gives us the probability of everything happening up to and including that point x. So let me get rid of my writing here. The CDF adds up or accumulates probability mass before a certain point, which is what I said before. I always get myself ahead of where my slides are. Okay. Now, The CDF also has conditions that sort of need to be met or are always true for CDFs, and those are that the CDF always begins at 0 and it always ends at 1. Okay? And so you may think, sort of where does that come from? It's kind of weird that we sort of got that out of nowhere, but if I add up, for instance, if I have like a 6-sided die, again, the example that we had before, there are probability masses at 1, 2, 3, 4, 5, and 6. And so the CDF at values of less than 1, which there are none, okay, I can't add up anything there, and so it's 0. If there's nothing to add up, the probability is 0. And if I add up, if it ends at 1, that means I've gotten through all the possible values of x. And because one of the stipulations of a PMF is that all of the values of the PMF have to add to 1, then because the CDF is adding up all probabilities less than or equal to a point, when I get to that endpoint, the last possible outcome, it should add to 1 because I'm adding together a PMF, which when I add them all together has to equal 1. Okay, so they're quite connected. So here's a quick example. I have the same example that we've been using, not in the your terms, but in my examples. And so we see we have here the PMF row. It's the second row. It's the probability that x is equal to an actual outcome. The random variable equals the actual outcome. I see that value. And then in the second row, or rather the third row, I now have my CDF line. And what that line, what the line is, these probabilities, you can see that each one is the probability that x is less than or equal to that value of x. So when we see our first value, 0, our PMF is going to jump up from 0. So before, like lower than 0, if we could go left, it would always start at 0. But we only start it in tables where we see the first value. So it jumps up to 0.05. And then if you look at 1, the CDF of 1, it adds up what it's at, 0.1, and previous, so 0.15. And then if you go on to the next one, at 2, it's 3. And so then what did I add up? Well, I added up everything at it or less. So 0.15 plus 0.1 plus 0.05, 0.3. And so you keep on going until you get to the end. And as promised, down here, the CDF ends at 1. It always has to. Okay? So that's just some parts of the CDF. So then what do I ask you here? I want you to answer the following questions. Okay, so what's the probability that at most 3 computers will be taken? Remember, our example is that we have a computer lab, we have 6 computers, and we want to look at each of the probabilities that anywhere from none of the computers are taken to all 6 of them are taken. And so the probability that at most 3 will be taken should indicate to us that we're looking for the probability that x is less than or equal to 3. At most means less than or equal to. And so how can we find that? Well, that fits the form exactly of a CDF. And so all that we need to do is go to 3 and then go to 3 here. Then look at the CDF value at 3, which is 0.55. And so our answer is 0.55. Next question, what's the probability that at least 4 will be taken? Okay, so, and these examples, of course, you can just use the PMFs as well in sort of real life, but for this question, I really do want you to use the actual CDF. So in the f notation, I'm really just looking for f of 3. Okay. What's the probability that at least 4 will be taken? At least 4. It's the probability that x is greater than or equal to 4. And so if we wanted to use the PMF, we would just add up 4, 5, and 6, and we would get the number, which is fine. But what we want to do is use the CDF. Okay, now the CDF, it gives us everything at or below a point. And so, in order to find greater than or equal to 4, we need to find another equivalent statement. And what I'm actually going to use here is, sorry, I got excited and wrote too much. We're going to use the rule that the probability that A happens is equal to 1 minus the probability of A complement. Okay, so this is the actual rule that we're going to use, which we saw in the last chapter to get our probability there. Okay, and so probability that x equals 4 is equal to 1 minus a probability, and the probability is A complement. So we have to think, what is the complement of greater than or equal to 4? And it might be tempting to say less than or equal to 4, but that's not quite true because we double counted the equals. It's in both sides. So really it's x is less than 4. X is less than 4. But that's not the form of the PDF. It needs to be less than or equal to. And here comes the sort of weirdness. This is equal to 1 minus the probability that x is less than or equal to what number? And so it's less than 4, okay, which is, there's nothing in between 3 and 4, so it's 3, 2, 1, and 0. And only, of course, those points. So I could actually rewrite less than 4 as less than or equal to 3. And I can do that because there's absolutely nothing of non-zero probability between 3 and 4. So it's the same thing. And so I could rewrite that 1 minus, what's the probability that x is less than or equal to 3? Again, we found that up above. It's 0.55, so 1 minus 0.55 is 0.45. And so that's the answer to that. What's the probability that at least 4 will be taken? 45%. Okay. Now when we move on here to the next problem, I've got to do some erasing. Sorry about this. Okay, that's good enough. What's the probability that between 1 and 6 computers will be taken? And here I want to go over two different situations, inclusive and exclusive. Okay, so inclusive and exclusive. Inclusive means that 1 and 6 are counted. Exclusive means that 1 and 6 are not counted. So let's do inclusive first. So what we're looking for is the probability that x is in between 1 and 6, but it's less than or equal to inequalities instead of just less than, because we're including the 1 and the 6. Now, of course, again, we could do this with the PMF because it's not that bad. We could just add those together. But I want to drive home using the CDF. So what we actually have to do now is we have to take the difference of two CDFs. Okay? Because the CDFs, they give us everything up until a point. So how do I encapsulate a between? And you might find it helpful to actually think of this problem as sort of a number line here. So if I've got my number line here, 1 and 6, I want to find what's in blue, which is between 1 and 6. Okay, and here it's inclusive. And so the first step in trying to sort of get that with a CDF would be probably to take the CDF of 6. And the CDF of 6, in which I'll squiggle in red, is we start at 6 and then we go all the way down to 1, and we keep on going, just indefinitely, keeps on going. And so what I've done by calculating the CDF at 6 is I've gotten most of what I want, but I've actually gotten some more. There's some extra there. And so I need to subtract away some. And what I need to subtract away is actually f of 1, right? Because f of 1, that encapsulates all of that extra part. And so f of 6 minus f of 1 is 1 minus 0.15. That gets us 0.85. And so the answer to that part is 0.85. Sorry if you hear my dog licking in the background. He's quite loud. Anyway, we're almost done. Exclusive means that we don't include those less than or equal to signs. And so it's between 1 and 6 exclusive. And so really, you can rewrite this as saying, like, what is the next closest thing to 6 that we are going to be interested in counting? And then what's the next closest thing to 1 that we are interested in counting? Because we're looking at integers, the next closest thing to 1 is a 2. And the next closest thing to the 6 is a 5. And so really, it's the same thing to say between 1 and 6 and exclusive, and 2 and 5 inclusive. And so we use the same argument that we did above, that this is f of 5 minus f of 2. Okay, and f of 5 minus f of 2 is 0.9 minus 0.3. And so the answer to the exclusive part is 0.6. So we see how inclusive and exclusive makes a difference. Now, there is one last one here, and I've got to do sort of a lot of erasing. And this one says, sorry, I'm just going to keep on going here for a while. What's the probability that at most 1.8 computers will be taken? Okay, and so this is also an interesting problem. Oh, sorry, yeah, okay, so there, all of it went away. The probability that at most 1.8 computers will be taken. Okay, and so you think this is a nonsensical answer because I can't have 1.8 computers to be taken. And so essentially, if I was up on this number line here, 1.8 might be here, and I want everything there and down of 1.8. But the answer to this problem is to rewrite this as the probability that x is less than or equal to 1. Because there's nothing from 1 to 1.8. So in blue here, from 1 to 1.8 in my blue box, there is no probability because any decimal can't happen. And so all that goes away, and a equivalent way to write less than or equal to 1.8 is less than or equal to 1. And we do know that from up here, it's 0.15. Okay, and so that is how to work with a cumulative distribution function. Okay, always try to write these, and I didn't do a great job, as sort of this F notation when you do the problems. Okay? So, your turn. This is the last your turn, okay, and we're end this video finally. Same experiment, rolling a 6-sided die. Okay, now I just want you to add not only the PDF but the CDF, okay, and then use the CDF to find these probabilities. And so you'll notice that those probabilities are, or the questions are very similar to what I just did. So hopefully it won't be so bad. Okay, I'll see you next time.